Remember how an electric motor works. Here is our very simple electric motor. We have a coil that we call an armature. This one is just a single loop and is one. And if we look at a proton right there, if we have a current coming through here, the proton is moving up the page. If you point your right thumb up your page, magnetic field points from north to south. Which direction will this proton feel a force? Yeah, this proton is going to feel a magnetic force that way, and it's going to feel on this side a magnetic force this way. But now we have a problem. Anderson, as soon as it starts to spin, not only is this proton moving up the page, I'll replace it with a red proton. The red proton, it's moving up the page, but it's also moving downwards because it's stuck inside the armature. So everybody point your right thumbs down the page. Magnetic field is still pointing to the right. Which way will that red proton feel a force? And the answer is against the source current. And same here, it's going to feel a force against the source current. That's in red. So what's going to happen is a voltage is actually going to be induced in the coil. The coil is going to act like a generator. We call this a back voltage or a back VMF. So I wrote down here, once the motor begins to spin, notice what happens. We can say this: by right-hand rule, the charge will experience a force backwards in the direction of the source voltage. But we should put in brackets, as soon as it starts to spin. While it's at rest, nothing. And we call this movement of charge a back voltage, or a back EMF, because it's an induced voltage, and we like to use EMF as our abbrev for a voltage that was created through motion, not through chemistry. Okay. Let's elaborate on this just a little bit. I'll wait, people are still writing. So let's elaborate on this a bit. What's the back EMF created by? The spinning of the armature. The armature is the coil that's spinning inside the motor. What is the back EMF amount proportional to? How fast the motor spins. In fact, I can also fill in C. When we're at rest, what's the back voltage exactly as a number? 0. And then so let's suppose you have a 20-volt source using a power drill. Right when you plug it in, right when you begin to hit the trigger to start it to spin, you would measure 20 volts in the armature. But as soon as the armature started to spin, it would send the voltage against that 20 volt, 19.9, 19.8, 19.7, 19.3, 19, 18, 17, 16. And the faster it spins, the bigger the back voltage, the smaller your net voltage, your overall voltage. In fact, when the motor is operating at its maximum speed, the back EMF is equal to the source voltage, at least in theory. What would your net overall voltage be then? If you have 20 volts coming in and you have 20 volts going in the opposite direction, if we use our ski hill analogy, if you take a chairlift up 20 volts and then ride the chairlift down 20 volts, what's your height? What's your net voltage? 0. Your net voltage is 0. So what's your net current then? Be stupid obvious here. 0. You actually have 0 amps going through the armature. So it says compare back EMF to the supply voltage. Well, I guess we would say this. At max V back equals V supply. That's in theory. It's never quite perfect because the universe doesn't give us a perfect system, but that's the theory. In fact, we can analyze this mathematically, I think. It says the mathematical analysis of this motor is fairly straightforward. If we look at our circuit diagram, here's our supply voltage, let's say 24 volts. So the current would be going in this direction. This direction is downhill. As soon as this motor starts to turn, it acts like a battery, a generator, but in the opposite direction of downhill. This little R right here, that's the resistance of the actual armature. So the thing that's turning, the rotor that's turning, has its own resistor. That's there. So the equivalent circuit for a motor includes the resistance of the motor coil itself, little r. Why do we use little r? We'd like that motor to have as little resistance as possible because we don't want to heat up the motor. The back EMF, V back, right there, and the supply or source EMF. Let's apply Kirchhoff's law. In fact, let's start right there. How high were we at the bottom of the chairlift? How many volts high were we once we got to the bottom of the chairlift? Who remembers? 0. So I'm going to say this. We're going to start at 0 equals. We're going through the supply voltage. So that's going to be a voltage gain. But then when we go through the back voltage, that's going to be a voltage loss because it's in the opposite direction. You would gain 24 and lose 3. And then there's also the voltage in the armature. Now, this is also a voltage loss, right? If we started with 25, we would subtract what we lose here. Don't write this down, look up. I'm going to start out by saying the voltage lost in the armature, but I'm not going to write it that way. V equals what times what? So instead of writing it that way, I'm going to say the voltage you lose in the armature is I in the armature times little r of the armature. And Chantal, all I'm going to do is get the back voltage by itself. How would I get the V back by itself? I would definitely just plus it over. This is our back voltage equation. The back voltage is the supply voltage minus I times R. Let's add some conditions. So the supply voltage is what you're getting from the plug of the motor or the battery of the motor. That's in volts. The back EMF is the one that's generated when the motor starts to spin. It acts like a generator because all motors are generators. All generators are motors. At rest, the back voltage is 0 volts. It's at its maximum speed. In a perfect physics world, its maximum speed, V back and V source would be equal, and so your net voltage would be 0, your net current would be 0. But it varies directly with the speed of the motor. As the motor spins faster, the back voltage gets bigger. Oh, and the maximum speed of the motor is when your back voltage equals your source voltage. It's not going to be able to go any faster. I is the current running through the motor in amps, and R, little r, is the resistance of the armature. I like example 3. I like example 3. Example 3 is a nice question. A motor is connected to a 100 volt supply. Hey, there's my V supply. Initially, with the motor at rest, this is going to be important, underline the word at rest, the current is 5 amps. When the motor is running, the back EMF is measured at 20 volts. Find, okay, Jesse, what does A want me to find? Okay, to do that, I'm going to use the idea that it's at rest. I am going to write my back voltage equation, V back equals V supply. You know what we often, well, V supply minus I times R. I'll just leave it like that. What does the question want me to find? Okay, can I? Let's find out. Before it's turning, when it's at rest, what's the back voltage exactly as a number, Jesse? Before it's turning, when it's at rest, what's the back voltage exactly as a number? Okay. What's the supply voltage? Minus, what's the current when it's at rest? What's the current when it's at rest? Read carefully. 5 R. I'm going to get the R by itself. I think I would plus the 5R over and then divide by 5. I think I'm going to find this. R ends up being 100 divided by 5. You don't need a calculator for that. What'd you get, Jesse? 100 divided by 5. Or you can use a calculator. What? Units? Resistance. Dude, you're slumping. We'll get you back here. Okay? What's B want me to find? When? Okay, so again, I'm going to use my back voltage equation. When I wrote this on your formula sheet, did I use V and V or did I use the EMF symbol for one of them? I can't remember. I put that there? Okay. What am I trying to find, Jesse? I'm going to get the I by itself. Now, I could, because there's a negative in front of the I could do the full swappy dance. You know what? I'm just going to get the I by itself. So I'm going to say this. The V back would drop down like a domino. I guess I would subtract the EMF. And then what? How would I get the I by itself? Harder. Divide what? I didn't hear. So you're telling me dividing the I would get the I by itself? I completely disagree with that statement, my friend. How would I get the I by itself? See, if I divide the R, don't write this down, write that down. This is what I have. I don't want to divide by R. You know what I really wanted to divide by? Yeah. That's why last year I taught you the swappy dance and we did that this year. We found it easier to just, the other thing I could have done is plus this to this side, minus the V back over and divide by, then I'm fine too. I don't care which way you do it, but folks, I will expect you to be able to get the I by itself. Let's crunch the numbers. I is going to be, Carter, what was the back voltage, the back EMF? They must have told me. I think they told me. I'll give you a hint. There's a sentence that says, when the motor is running, the back EMF is measured as. Okay, don't overcomplicate this. So did they tell me the back EMF? Hey, yes. Okay, it's going to be 20 minus, what was the source voltage? The source EMF. Supply, yep. Divided by negative, what was R? In fact, Joe, you might be able to do this in your head because I'm pretty sure it's negative 80 divided by negative 20. What's a negative divided by a negative? What's 80 divided by 20? What's 80 divided by 20? 4. People. Carter, units? Amps. Before you turn the page, what happens if I run this motor faster? Well, then the back EMF gets bigger, which means the top becomes this minus that smaller because we're subtracting. We get a smaller current. The faster you run it, the lower the current. Example 4. Example 4. Wants me to find, by the way, I would have no problem, example 3, asking you part B and expecting you to clue in, oh, I need to find the resistance of the armature. Oh, they gave me enough to find that. That's probably what I'll do. The resistance of the armature, example 4, is 12 ohms. At operating speed, when connected to a 120 volt outlet, the motor draws 6 amps of current. Oh, okay, Alfie, what's this want me to find? Oh, this is the source voltage. Do I know the source voltage? What? Do I know the current? Do I know the resistance? This is straight plug and chug. It's going to be 120 minus 6 times 12. I'll have a back voltage of 48 volts. 72 volts are still turning the motor and causing it to speed up. 48 volts are being canceled out, are canceling out that 120 source voltage. Some of it at least. So when an electric drill is prevented from turning, the motor heats up. How can we cool the motor off? This is something all of you should learn because you'll be using battery-powered tools, I suspect, as you adult. So if I'm trying, yeah, take it off of load, hold the trigger down. Yeah, it's weird. You cool it off by revving it to its max. Why? Because then the back EMF equals the source via EMF. What's my net voltage overall? What's my net current overall? And you know what causes heat? Current. Because that's the electrons moving through. And as they bump into things, they give off heat. So yeah, good. Remove the drill from load, and run it at full speed. Yep, that'll work. The back EMF of a motor is 4.2 volts when operated from a 6 volt source. When held stationary, this is going to be really, really important. The current is 5 amps. Okay. Gibson, what's A want me to find? Okay, they've talked about back voltage. I'm going to try writing out the back voltage equation. And I'm going to get the R by itself. Gibson, do you want to do the swappy dance to get the R by itself? Or do you want to just end up dividing by negative I to get the R by itself? I don't care. It's the same old pick. Okay, so Gibson says, I know I'm going to get the R by itself. What's right in front of the R that I don't like? A negative. Blech! Swappy dance. So I'm going to move that there, move that there. I get positive I times R equals source minus the back. And I forgot to put it back here. Okay, how would I get the R by itself? Oh, which situation am I going to use to find R? When it's stationary or when it's turning? When it's stationary. Why? What's my back voltage when it's stationary exactly as a number? Nope. What's my back voltage when it's What? And so it just ends up being source voltage 6 divided by current 5. This has a resistance of, I could do this in my head, I'm pretty sure it's 1.2, but double check me. Anyone else? Yep. Units, it's resistance. Okay. I think in the previous question that I said I kind of liked, oh no, this is very similar to example 2 or whatever it was. I like this question. Part B. Now, what's the current when it's rotating at its normal speed? So again, I think to myself, back voltage is source voltage minus I times R. Anderson, what's B asking me to find? So which variable is that in my equation? Which of these is current? The V, the E, the I, or the R? The I. So I'm going to get the I by itself. Do you want to swappy dance first, or do you want to swappy dance first? Okay. Plus that over, minus that over. And we get I times R equals source voltage minus V back. How would I get the I by itself? I'm not quite. It's not the radius. What's this little R stand for? And don't feel bad. I've told you from day one last year, we need more letters of the English alphabet. We don't have that. What's this R? Yeah, why is it a lowercase r? Because we want the armature to be really tiny resistance. Otherwise, the motor would just heat up no matter what. Okay. Here we go. What was the source voltage? What was V back? The back EMF. Sorry? 4.2 divided by R, 1.2. What do you get? This might work out nice. Yeah, you're going to get 18 over 12 divided by 2 divided by 2. That's going to be 9 over 6, 3 over 2. Oh, is it 1.5 units? Amps. Okay. And again, there's a good chance on the test I wouldn't ask part B. I start part A, I jump straight to part B, and I expect you to get this far and say, I don't know the resistance of the armature. Oh, they told me that when it was stationary, we had 5 amps. Stationary means I also know V back, 0. I can find the resistance of the armature. Some neat applications. So those of you that have electric cars, this is how regenerative braking works in your electric vehicle. When you take your foot off of the accelerator, there's no current flowing from the battery through the motor, but the motor is still being turned by the wheels. It's generating a back EMF back against the grain and recharging your battery. It's more complicated than that, but that's the gist of it. And we can almost come up with hoverboards, but I'm gonna have to pause the video first before I show that one. Magnetic levitation is cool, but also induction cooking. Does anybody here have an induction cooktop in their house? And a couple of students in my other block. They're slowly making their way to North America. They've been big in Australia for quite a while because an induction cooker cooks by heating a pot up with a changing magnetic field. which means no heat escapes around the edge of the pot. You can see here we have water boiling, and right next to it on the same element, ice cubes sitting just fine. And it also means, for example, if you have young children, they can't burn themselves on the stove top. Any heat the stovetop picks up would be conducted from the pot, but it's nowhere near what a red hot element is. So how does it work? First of all, your cookware has to be conductive. An easy way to check that is to see if a magnet will stick to it. These are also becoming popular in dorm rooms that aren't outfitted with a kitchen. You can get a single plug-in induction cooker, but you have to make sure you buy cookware that has some magnetism in it, is ferromagnetic. Then all that happens inside the device, there's a very rapidly changing magnetic field. And so that means you have a very rapidly changing flux in the cookware, which means Lenz's law kicks in. You're creating eddy currents in the cookware, but because the current is oscillating, those eddy currents will oscillate. You have electrons moving this way, clockwise, then counterclockwise, then clockwise, and in the same way as you can generate heat by rubbing your hands together, the electrons bumping into each other generate heat. It's a really pretty efficient way to do some cooking. Really quite nice. So induction cooktops, another nice example. What's your homework? Here's what I assigned my block G's. It's probably going to be easier to cross out questions. You can cross out number 3 and number 4. Cross out number 3 and number 4. So you can do number 1, number 2, cross out 3, cross out 4. 5 is good, 6 is good, 7 is good, 8 is good. You can also technically do any question on the ultimate review that doesn't have a transformer in it, for what it's worth. Let me hit pause.